is an example in number theory. People who study number theory study these kind of functions. They are what I call arithmetic functions, just as sin x, cosine x, and so on. But sin x, cosine x, x can be any real number. Here, these functions are defined over integers, in fact, natural numbers, and they are arithmetic functions because they will satisfy something like a Mobius function of a product of two prime numbers is equal to the product of the Mobius function on those prime numbers. So mu of P1, P2 will be equal to product mu P1, mu P2, etc., etc. There are all of these kind of properties which are in general arithmetic properties. But the important message which I wanted to give was that here is a very simple function. It appears to be random and unpredictable in some sense. So that is one of these functions, and in fact, what will happen if we sum these things up? It looks like there will be cancellations. 1 plus minus 1 is 0, then minus 1, 0, minus 1, 1. It looks like maybe it's going to go to 0, and that function, if you sum this Mobius function up, n terms of the Mobius function, is called a Merton function, and here I plot these things. Those of you who haven't used, there are very nice software such as Mathematica or some MATLAB and so on, which can do this very easily, or you can do it in Python, which is freely available. Things, and then you can see how this Merton function now oscillates. It seems to be pretty much like 0, but again you see how complicated it starts to look, this simple function. But this is only till about 100. If we go till 1000, which you can do quite easily, there is this kind of oscillations which are certainly not periodic, but they seem to be actually growing with n. They seem to be growing with n, and Merton conjectured that this absolute value of the sum is actually less than square root of n. Again, you can ask, how is this growing with n? And he conjectured that it's always smaller than square root of n, which seems like a very reasonable conjecture, right? I mean, you have n is 100, nothing has crossed square root of 100, which is 10. 1000, nothing has crossed about 30 or so. So it seems like this is more or less true, that this m of n is growing. If at all it is growing, it's growing at a rate which is smaller than square root of n. In fact, there were no counter examples. There were no counter examples for less than n less than 10 to the power of 30. Huge number. But actually it is incorrect. So we sometimes do things where we say that prove something, we prove it for n is 1, 2, and then we assume that it is true for 3, etc. That's of course not a proof, and this is a very bizarre example where 10 power 30 times you're correct, but you're wrong actually speaking. However, it's incorrect. And in fact, if anybody proves that there exists a constant c such that this Merton function is less than c times square root of n, there's a constant c such that this is true, then this is equivalent to proving the Riemann hypothesis or the Riemann conjecture. So it's a way, it doesn't look like this has anything to do with the Riemann, the zeros of the Riemann zeta function, but actually how fast this function grows is determined by this. And the square root of n, let me say that the square root of n is something very interesting and important also from point of view of physics. And this m of n, you may think about this mu. Let's do this kind of a game. You start from somewhere, let's call that point 0. you start from somewhere, let's say we'll call that 0, and if there is 1 there, we will move 1 step to the right, okay, and then there is a -1, we'll move 1 step to the left, and we are back where we started. So that's exactly what m of n is doing, right? It's just adding things, and then again -1, so it's moving there, and if it is 0, you don't do anything, and then you play the game like that, 0, -1. So this looks like a person who is like a drunken person who is walking on this line. Sometimes he walks to the left, sometimes to the right, and sometimes doesn't walk at all. And the question is, how far is this drunken guy going to go in a time n? If he is not drunk and is just going 1 step to the left, like what we saw at the beginning of natural numbers, he is going to be at n. But if he is doing this kind of a dissipative thing, that he is going left, right, he is going to go, that's what Merton function says, approximately as square root of the time. So what he could have gone as, let's say 100, he is only at 10. And in fact, in physics, this square root of time, the growth of square root of time, is called diffusion. So normal diffusion. It's called normal diffusion. Somebody mentioned an ink being dropped into water. How is this ink going mixing into the water? Is actually quite a complicated thing, but a very simple model of this is like this. So it looks like the Mobius function is doing a random walk. Such like things are called random walks. But there's nothing random about this walk. This is actually more like a Mobius walk. Mobius walk. But it's looking like random walk. Okay, and then there is another function called so this is not the only function. There are other functions, arithmetic functions. This is a Liouville lambda function, which takes only values plus minus 1, which is simply -1 to the power of number of prime factors that it has, including multiplicity. So it's basically the sum of all those A1, A2 that I wrote down. So lambda of 8 will be 2 to the power of 3. There are 3 factors of this prime number 2, so it's -1 to the power of 3, it's -1. Lambda of 6 is 2 times 3, that's -1 to the 2 prime factors, including multiplicity, that's only 2, so it's +1. There are no zeros in this. Now this is like a random walk in which there is no rest for the guy, so it just goes 1 minus 1. Again, it's looking very random. You can plot this lambda n, and its connection to the Riemann zeta function is like this, that it is Riemann zeta to the 2s divided by Riemann zeta to the s. And if you look at how that growth is going to go, see, this is 1 minus 1 again. It looks like it's going to add to 0, but it's not. It seems to be drifting into the negative side. So the growth of these things and the behavior of these are actually very challenging questions, and you can see how random this is looking with all these oscillations. All of that is coming from this very simple arithmetic function, and you can see that all of these things are connected to the prime numbers, and therefore the disorder in the prime numbers or randomness in that is being reflected in this. At the same time, there's a lot of order. Okay, I think I'll skip this because but these are interesting formulas. So product of cosine x, cosine 2x. I think those of you who are, can all of you prove this formula? It's a simple formula. Please write it down and don't try to prove it now. You can do it as an exercise if you don't. Anybody already knows or has an idea? Yeah. You will multiply by sine x here. Yeah, you multiply by sine x, and then what identity you will use? Sine 2x, and then there is cos 2x. So again, So that is happy, and it becomes sine 4x, and then there's a cos 4x, and then it becomes sine 8x, etc. So you can see that it's sine of 2 power n plus 1x divided by 2 power n plus 1. Very simple, very beautiful formula. Now you plot this as a function of x, and you will notice that there are these peaks at pi by 2 and 0. There are these peaks at 0, pi, where actually this numerator and denominator both vanish. It's going to go, it diverges, otherwise it's 0. It's effectively 0. So it's a very simple function. It doesn't look anything like these complicated function. That's my point. Now, you guys, a lot of you solved this thing. Now, let's replace this by sin x instead of cos x, sin x. Anybody has a guess how to do that? Sin x into sin 2x into sin 4x. I don't expect you to. So if you multiply by cos x, let's say that we multiply by cos x, what will you get? You will get sin, you will get sin 2x, but then you will have another sin 2x there. Doesn't help you. In fact, the trick doesn't work, and that function is much more complicated than this function. It looks like this. Plot it, okay, and you will see that the larger the n is, the more intricate the structure becomes. And if you look at this function, it has very interesting properties. I mean, if you look at maybe this one, and if you look at it closely, you will see as if this whole thing is there. So these are examples of multifractal functions, fractals and multifractal functions, in which they are not, especially as n goes to infinity, this is a very oscillatory function which can appear to be very random, and behind this function there is of course simplicity, and there is also a sequence behind this function. That binary sequence is called a Thue-Morse sequence. This sequence goes like this: 1 minus 1 minus 1 1. So do you see order in this sequence? Unlike the Liouville thing, I claim that there is actually order here. Can you tell me what that order is? I've actually written it down here. You start with 1 and you append to 1 its negative. So 1 minus 1. And then you take these two numbers, 1 minus 1, and then you append to it its negative, which is minus 1 and 1. Okay, you get this. And then you have 4 numbers. And then you take these 4 numbers and you append its negative, you get this. And so you get this sequence called the Thue-Morse sequence. Clearly there is a rule. So here is the rule. So you take A to AB, B to BA. So if you start from A will become AB, A will become AB again, B will become BA, and so on. So you will get a sequence of A's and B's, and this sequence is not periodic. It looks like a very simple rule, yet it's not periodic. There are very many interesting properties of this sequence. You can Google this if you want to understand this better. And the connection to this function, I will leave that for you to explore, the connection of this to this product of sines and the Thue-Morse sequence. Okay, so because I want to get into some physics, it looks like a mathematics lecture so far, but I want to also touch on some physics aspects. But are there any, so this is like part 2, so are there any questions or comments about what we have said so far. Okay, so Newton's laws. So we'll get into the realm of nature of physics as such from the more abstract world of mathematics. Of course, they are all connected. Mathematics is the language of physics. So Newton's second law, you know, that force is proportional to the acceleration, and you can write it in terms of a differential equation because this acceleration is the rate of change of the velocity. Velocity itself is rate of change of position, so it's a second derivative of the position vector m. So given a force F, we have to solve for this to find out position of the particle according to Newton's laws. Now, this person, I don't know whether you guys still read these comics called Tintin. So if you do, what's this guy's name? Yeah, Professor Calculus. He has this pendulum for some weird reason. And a pendulum is one of the simplest examples we study in mechanics. I hope you guys all do experiments you would have done experiments with a pendulum, right? What experiment did you do? Huh? Measurement of acceleration due to gravity. How did you do that? Time period, yeah. So time period is given by what? What formula do you? 2 by root of L by G. Pendulum of length L, there is gravity acting on it, there is this force mg, there is this angle theta that it is suspended to. But if you apply Newton's laws, the force that's going to act on this is minus mg, the torque that's acting on it is minus some mgl sine theta, and therefore this is the differential equation which you're getting if you solve that. And this is the energy of this pendulum. This is the kinetic energy, that is the potential energy, and that's the total energy. Okay, maybe So this pendulum motion is actually rather regular, right? You know that there are these oscillatory behavior, it just oscillates. So in all the sequences which we talked about in the first part, it appears to be a very simple sequence in which if you look at this position as a function of time, maybe it's starting from somewhere and then it's oscillating. So it's like this periodic motion, and another very famous periodic motion is coming from Kepler's laws, and where there is this gravitational problem of two bodies which are attracting each other due to gravitation, and Newton's laws of gravitation, like the Earth and Sun system, or a satellite moving around the Earth. And the time period of this is related to the distance to some kind of, it's going to move. We know that it's moving in an ellipse, and corresponding to its ellipse, some semi-major or semi-minor axis, you can write down the time period to be given like this. So here also it's a periodic motion of this planet, or the satellite around the planet, or the planet around the sun. Why are they simple? You can ask this question, how come the pendulum is simple? How come Kepler's laws, how come the motion of the earth around the sun is so simple? The pendulum has only 1 degree of freedom. What does that mean? A degree of freedom is the minimum number of coordinates you need to specify the system. Coordinates is simply position. not the velocity, just the position. So clearly for the pendulum, if I specify this angle theta from the vertical, I'm done, right? You have to think about degrees of freedom as how many coordinates, how much of freedom do I have to specify the configuration of that system. And it has only one. The Kepler problem actually has 3 degrees of freedom because it's, let's consider what do I mean by Kepler problem? Let's consider the sun, heavy mass, and earth. So this is, let's say, fixed, and this is moving around like this. So this position of the earth, there is x, y, and z with respect to some coordinate system. Let's say the origin is the sun. So it has 3 degrees of freedom, but actually there is a lot of symmetry in the problem, especially rotational symmetry, that there is effectively only 1 degree of freedom. Okay, so that's what restricts this motion to lie on this ellipse. So how can there be complicated dynamics in nature? So we kind of started out by saying that we can't predict a coin toss, cannot predict the weather, cannot predict heart attack, stock market, or turbulence, uncertainty and turbulence around us. So beyond regular dynamics, we have to look at systems which have more than just 1 degree of freedom. Maybe that is a clue. The other thing is nonlinear equations. Equations such as the simple pendulum, which you derived this 2 pi square root of L by G, you all would have been told that theta is small. Don't put the pendulum more than, I don't know how much, 9 is it? Depends on the school, I think. So 9, 4, 5, whatever, right? So they'll warn you, don't go more than that. What will happen if you go more than that? What won't work? Approximation won't work, but the pendulum will work, right? Pendulum will continue to work. For deriving this time period, indeed. So let's look at this equation of motion. This is a nonlinear differential equation because there is theta, there is sine theta is not a linear function of theta. Linear means like a straight line. So it's not. Sine theta is not a straight line. So it's sine theta equal to 0. This is the true equation of the pendulum. This is approximate equation of the pendulum from which you can derive this time period. But my question is, suppose this angle is larger than theta small. Okay. This formula will not hold, but will there be still a time period? Yes. There will be a time period. What will happen to the time period? Will it be larger than this, smaller than this? Any guesses? There are only 2 possible guesses. You'll be 50% correct according to our, if it's a random process. Okay. One guess is smaller. How many people think it will be smaller? Everybody has to vote, otherwise no lunch. Smaller. Why?
Because as theta increases, it will go up to 5, but sin theta can only go up to 0.
Sin theta can go, minus 1 to 1. Okay. You're saying that theta can be very large, so but sin theta is actually you're correct. Sin theta is smaller than theta, but so what? How does that imply that the time period decreases? Doesn't follow from that. How many people think it will be larger? Why? Why do you think it will be larger? Just a guess. Yeah,
Sir,
louder.
For a very small value of theta, the theta value is sin theta when it's approximated to the value of theta will get a greater value when we substitute in the equation. Sin theta can maximum be 1
yes.
and it won't go to negative values. So our equation will also
No, it
have
can
a
go negative, why not? Theta is oscillating.
Yes sir, but when theta becomes, we'll get a larger value of theta when we substitute because sin theta can maximum go to 1 or minus 1.
Okay, these seem to be some kind of, is there other arguments which are based on some kind of physical arguments rather than sin theta? Yeah.
So how do we know that we're keeping theta as a constant?
How do we know what?
When we're doing the experiment, we can accidentally change the value of theta. So how do we know that we can keep it constant?
What constant?
Theta
Theta is
value.
not a constant. Theta is changing in time. Yeah. But you can release it from larger and larger angles, the initial angle. That's what I'm asking. You can release it, if it's a thin rod rather than a string, you can release it from 90 degrees or larger than 90 degrees, right? Yeah. Okay. Yeah.
Pendulum is being released from very high angle, it may not even follow the normal harmonic motion, like go under such irregular motion. And also, as you suggested, if we use a rod or something, it wouldn't be simple anymore. We have to take into consideration the center of mass and so many other things. So maybe this equation itself doesn't apply for that.
No, let's take, okay, we can look at it, but actually this equation is pretty general. Even you can look at solid rods, but you can make, we are all physicists, physicists tend to make these kind of assumptions. They'll say massless rod and there is a mass there. That is the approximation that is made. So actually, physically, you can just take a pendulum, and I have a pendulum right there for you to see that. So maybe this is not a simple pendulum. It's somewhat different, but let's just keep this fixed. So what I'm saying is, what you're saying is that you have done this experiment. I'm saying, do this, actually this is not a very nice pendulum. It's got a lot of friction. So any guesses? This is actually pretty bad. So I had a good pendulum, like calculus did, but got stolen by some students, and they made me, not stolen, lost by some students. They made me a new one and gave it to me a few days ago. Unfortunately, it's not that great. But the point is that actually this time period increases. The time period increases, and the answer might surprise you. The time period increases as the amplitude increases, and actually it goes to infinity. It goes to infinity as the angle is going to pi. So if you plot the time period versus the amplitude, initial amplitude, let's call that angle theta 0, your famous 2 pi square root of L by G is here. It will start from small angle theta equal to 0, maybe 5, 6, it will hold, but actually these are all approximations. It's going to grow to infinity at theta is 0 is pi. And why does it go to infinity? Answer is actually very simple. If you start from here, if you start from pi, what will happen? Yeah, in reality it will fall, but if according to that equation, it will stay there because it is an equilibrium point. The forces are equal to 0 there, and you are starting with 0 velocity, therefore it remains there. This is an equilibrium point. This is also an equilibrium point. But there is a difference between this equilibrium point and this equilibrium point. What is the difference? Unstable versus stable. The fact that there exists this period is infinity. If I'm here, I'm going to wait forever. Of course, you may say that I can wait for zero time also, but actually the fact that there is this unstable equilibrium point there at pi is what makes the period infinite. So this period goes to infinity. So you see the nonlinear, this is an effect of the nonlinearity. It's coming from sine theta. And there is, although the behavior is still periodic, this pendulum has too much friction to see the periodicity, but it's actually just periodic. The period increases and increases to infinity. And this is an effect of nonlinearity. There are two equilibrium points. There are two types of motions. Oscillations like this, and also if I give it sufficient energy, not really very good again. I can only see a few rotations, right? So those are rotational motions. So there are two types of motions. So, okay, let me not go into more sequences. I think I don't have the time for that. So let me go this double pendulum. So this one won't work for me, this PowerPoint. None of these simulations are going to work. But this is, now let's go into this. I was holding this all the time. Now let's go into this. What is this now? How many degrees of freedom does this have? 2 degrees of freedom, because there are two angles I have to specify. This angle here and this angle here. They are two independent things. So we've gone from 1 to 2. And believe me, physics is not the same. Okay? A lot of people, and I've seen many mature physicists, seem to think that it's a matter of maybe having one more differential equation, or that's not the case. Qualitatively, there are completely different things, including now what appears to be chaos. So now let's give a very large amplitude to this, and I will ask you to observe what happens. So, as I said, unfortunately, this pendulum is subject to a lot of dissipation and friction. So, what's happening is it's getting stuck finally in a rather simple oscillation, and this simple oscillation is called a normal mode, which you have. But before it does that, I want you to especially observe the small guy, the small pendulum. Can you predict what it's going to do? So, I mean, when you think it's going to go in one direction, it starts to go in the other, right? So, in fact, the chaos which I was talking about and the randomness which I was talking about this is an example of that, especially when you give it a lot of energy. Okay, so that's why I'm giving it a lot of potential energy. I've also given it kinetic energy by way of pushing it, and there is a transfer of energy between these 2 degrees of freedom. There are 2 degrees of freedom, this big rod and the small rod, and there is this larger rod that doesn't seem to be rotating much, but actually conserves a lot of energy. It has a lot of energy and it exchanges with that. And how does this randomness come about? It comes about, how you can see it, observe it, is that if you release it from the same position, let me try to release it from approximately 90, this is 90 degrees, that's 0. Okay, this one seems to be getting stuck already, too much friction. Let me try to do it like this, okay. So, now if you try to record, anti-clockwise, clockwise, how many rotations the small one is doing. You want to try? I don't know how much time you have. Okay. Try this. Okay, I'm starting from here. You have to observe, each of you independently. Observe the small guy and see clockwise rotations, how many times it's doing, by full rotations I mean, and then anti-clockwise, and then it's switching from clockwise to anti-clockwise. Let's try to do some experiment like that. Are you ready? Are you ready? All right. Nobody is writing. Okay. Let's say that it died. Tell me. Anybody?
Approximately 6.
6 what?
Rotating around the
You have to also tell me, first it went clockwise so many times. You guys are going to be scientists, I think, right? I mean, how do you record? Again, scientists keep doing the same mistake again and again. I'm going to release it once more, okay? Are you ready? I did. So it's not much. Yeah, tell me. Huh?
14 each.
Each means what?
Roughly 14 each.
Huh? 8 clockwise, 8 anti-clockwise. You also got that. And then what happened? That's it. 8 clockwise, 8 anti-clockwise. And then 14 was what? That's a very different number. I don't know whether girls and boys get different answers. So, okay, we'll try it once more. Same thing, okay? But even according to me, it's flipping many times. You have to also note down that it's flipping. It's going from anti-clockwise to clockwise. How many times did it flip?
Around 14, 15 each. Yeah.
Okay, now these look like random numbers, you see. So we have found our random numbers. So the point is also the following. Each time I do this, you will get a different answer. See, we come back to this question of why I cannot predict a coin toss. And you did tell me, some of you, that look, you're not going to do the exact initial conditions. Similar here, it's actually that there are slightly, although it looks like I'm doing it from the same initial condition, it's clearly not. There can be slight differences, and those slight differences are enough to give you completely different futures. So this is an example of a chaotic system. So just chaos can come, chaos, which looks like apparent randomness. Equations of motion can be written. Newton's laws are perfectly valid. You have theta 1, you have theta 2, you can write down differential equations for that. You may not be able to right now, but you will in the future be able to write it down. They are quite simple. So you can analyze the forces which are acting on this. At the same time, you have actually pretty what are called chaotic motions. Okay, so I have here some very simple models in which you can study these kind of chaos, but I think I'll skip that. There's something called a logistic map. This is not the equations of the pendulum, but much more simpler equation, such as this kind of equation. Let me just write it down. So the study of these kind of things, but maybe I will first write down. So the simple pendulum, you know, it's called a simple pendulum, 1 degree of freedom. It's got 1 degree of freedom. There are these, it contains oscillatory motions that are periodic. And its period t is growing to infinity because there is an unstable equilibrium point. And if you do anything to this pendulum, because of this unstable periodic point, unstable equilibrium point, and the nonlinearity in the system, it can get into things which are looking random and chaotic. For instance, this is one of the things which I have done. I have attached a pendulum to another pendulum, a double pendulum, and that unstable point, around that unstable point, will start complicated motions which people now call chaos. But you can do other things. For example, you can take this pendulum and you can start jiggling. You can attach it to a motor or something and change the length of the pendulum periodically with time, up and down, up and down. That will also be sufficient. It's called a forced pendulum. It will also go into chaos. Almost anything you do to a pendulum, it will go into chaos. And that's because its degrees of freedom increases. The double pendulum or higher, you can go to triple pendulum also. There are all these simulations. So 2 degrees of freedom. It has chaos. It can also have periodic, so it's not as if everything here is chaotic. Low energy oscillations are actually periodic. Low energy oscillations, where again you can approximate theta to be sine theta to be theta, small oscillations. Even though there are 2 degrees of freedom, these things are not chaotic. But once you have nonlinearity significantly affecting it, things can be quite different and can lead to chaos, high energy oscillations. Okay, so there is sensitive dependence on initial conditions. So sometimes in popular literature, it's also called butterfly effect. Butterfly effect. Because there was also a movie by that name. Because one of the first people who formulated this in the 60s and 70s, there's a lot of mathematical work, and with the advent of computers, people could study these things numerically. You can't solve them analytically typically. You can't solve them that well. The butterfly effect came to be the case when I said that the weather, so it's actually a model of a weather that somebody was studying, a person called Lawrence, in fact, not the Lawrence that with a T, 1960s, maybe 63 or so. He was studying a model of a weather, and he found, when he was integrating those differential equations, he found such chaos in the solutions of those differential equations. And to express this sensitivity to initial conditions, he said, look, if you change the initial conditions slightly, the weather can completely change, the result can completely change. And so he said, if a butterfly is flapping its wings in Sao Paulo or something, it can change the weather in Beijing. So that's the small effects can have very large consequences. Of course, that looks very drastic, but that is why it's called the butterfly effect. You might have heard about it. So there is a lot of work around that. So this is a simple model for this kind of behavior. So let me, I won't go into the details of it, but it's called the logistic map. You can see this. There is now just one x, n is time, now time is discrete. It's a simple model. Okay. And what is the rule? The rule is you take x of at time n, multiply it by 1 minus xn and some constant r, and you call this x at time n plus 1, the next time. So the next time is determined completely by the present time, and this value r is your parameter, and this is called a logistic map. It's a very simple thing which you can do in your computer immediately, and you will see these kind of pictures of x versus time. So if r is small like 0.5, it will just decay down to 0. If r is larger like 1.5, depending on where you start, it doesn't matter where you start, after some time it will become a constant. So depending on where you start between 0 and 1, by the way, I should have said that all this x, you start between 0 and 1, you'll remain between 0 and 1, and it will just go to this constant. If you increase r even further, like 3.2, you will find oscillations now. You will find period 2 oscillations. You can see that you have these oscillatory behavior. 3.5, you'll have period 4. 3.8, it doesn't look periodic anymore. You see, this is again such a simple equation, but you get into things which start looking now like the Mobius function. R equals 4 is the extreme case where you can actually understand and solve things mathematically. You can solve it exactly. Still, it's completely chaotic and it appears to be irregular. So here is an example, mathematical example, it's nonlinear. Xn into 1 minus xn. Xn square is nonlinear. So it's got sensitive dependence on initial conditions. If you start from 2 points that are very close by, I've plotted 2 things here, blue and red. Initially you don't see the difference between blue and red, but after about 20 you can start seeing the difference clearly. There won't be any connection between the two. So I start with something like a difference of 10 power minus 6. After 20 time steps, it would have gone to order 1. Okay, so I think I will stop here. By the way, this is the Lorentz equations which I was talking about, the weather equation. There are 3 differential equations and they have this butterfly effect. So it's very interesting. I pointed out the product of signs gives rise to multifractal sets. The study of chaos is also aesthetically pleasing. You get very interesting mathematical objects such as these in higher dimensions. But let me actually end here because my time is up. Brief history of chaos. I mentioned the Kepler problem, but Kepler, we're not alone. The sun and earth are not the only object. You have the moon, you have Jupiter and so on. Actually, the 3-body gravitational problem is also having chaos. It is already chaotic, and that was already analyzed by Poincaré at the beginning of the century. And then there's a very fascinating history of what is chaos. Okay, so I will not stop. I will not talk about this. So simple laws can lead to complicated dynamics. Chaos is not at all uncommon. Nonlinearity leads to interesting phenomena, and you can explore many of things on your laptop. So with that, I will conclude. Yeah, thank you. Any questions you may have, I can take. Oh, hi. There's a question. Huh?
Art application where it is used.
Applications. Good question. Application of what?
This concept of chaos.
Anything which is nonlinear, and everything is nonlinear, and anything which has more than 1 degree of freedom is chaotic. So science has to, our object is to, that's how I started also. I kind of motivated for us to understand where does all this randomness arise from. And then we can try to then predict better. So what I've tried to tell you is that even simple laws can give rise to random behavior. After that, you can try to control it if you wish. If you think you don't like it, you can control it. So control of chaos is a big subject. So you will have, like for example, also the weather, right? Let's say actually the weather is showing this kind of chaos. Then how do you improve the prediction? Once you know that something is chaotic, how can you improve that? Can you control it? That's another kind of thing. Then there are very beautiful subjects called synchronization of chaos. You can have things which are looking very chaotic like pendulum, but both of them, there will be two of them which look exactly the same. They'll be synchronized, although they'll be sensitively dependent on initial conditions. So yeah, I mean there's a whole host of things, but it's not like a product or something. But yeah, I mean that's in physics it's a very basic thing. So like if you ask where is the two-body problem applied, you may say satellite. When we're sending out satellites, maybe we need to know Kepler's laws. We need to know all of these things too. We need to know about the existence of what happens when there's a third object. So it's basic physics and mathematics. Yeah.
It is my honor to deliver the vote of thanks for this lecture. Thank you, sir, for providing us with your valuable time and effort. I'm sure all of us will periodically review your work, and this lecture will give us a cascade event in our lives. And I would also like all of you to give sir a big round of applause for his work.
Thank you very much, and may the chaos be with you.